How do custom bootloaders enable remote firmware upgrades? Imagine being able to update your electronic device's software from miles away without ever opening it up. That's what custom bootloaders make possible in embedded systems. They are tiny programs stored in a microcontroller's non-volatile memory, which is memory that keeps data even when the power is off. These bootloaders act as gatekeepers, managing how new firmware gets into the device remotely. They sit between the hardware and the main application firmware, making sure updates happen smoothly and securely. When a device powers on, the bootloader runs first. It checks if there's a request for a firmware update or if it should just start the main program. If an update is needed, the bootloader listens for data sent over communication channels like Universal Serial Bus, Universal Asynchronous Receiver Transmitter, Wi-Fi, or other wireless protocols. These data packets are small chunks of the new firmware, sent step by step. To keep the transfer safe, the bootloader uses error detection methods like checksums or cyclic redundancy checks to verify that each packet is correct. Custom bootloaders handle several key tasks to enable remote updates. First, they set up the communication interface, initializing hardware peripherals such as USB ports or Wi-Fi modules. This allows the device to receive new firmware over the air or through wired connections. Next, they manage the device's flash memory, which is where the firmware is stored. They carefully erase and write new data, often using dual memory banks or partition schemes. This way, the current firmware remains untouched until the new version is fully received and verified, preventing the device from becoming unusable if the update gets interrupted. Once the entire firmware image is received, the bootloader performs verification. It checks the integrity of the data using CRCs or digital signatures. This step ensures the firmware is not corrupted or tampered with, which is vital for security and reliability. If the verification passes, the bootloader updates internal flags or memory locations to mark the new firmware as active. It then jumps to the main application start address, launching the updated firmware. If verification fails or the update is incomplete, the bootloader can revert to the previous firmware, keeping the device operational. In practical applications, such as with microcontrollers like the STM32 series, custom bootloaders are designed to support remote updates via USB or Wi-Fi modules like ESP32. They handle all the communication, flash programming, and verification steps automatically. Writing a custom bootloader in embedded C language involves low-level programming, directly controlling microcontroller registers for peripherals and memory operations. It also requires designing reliable state machines to manage the update process, error handling, and recovery. In essence, custom bootloaders make remote firmware upgrades possible by creating a controlled environment that receives, checks, writes, and activates new firmware images over various communication interfaces. They ensure devices stay up to date, secure, and functional without needing physical access. This capability is fundamental for maintaining, updating features, and patching security issues in modern embedded systems.